Everyone, welcome and thank you for joining us today. So today we'll discuss how graph neural networks can help financial institutions detect hidden mule networks and fraud rings that are difficult to find with traditional rules, transaction monitoring, or isolated machine learning models. So fraud rarely happens in isolation. Mule accounts, devices, emails, phone numbers, merchants, banks, transactions, they're all connected. Individually, each account or transaction may look normal, but when we analyze the relationships across the network, hidden patterns start to emerge. So this is where graph becomes powerful. Tiger Graph allows us to model these relationships directly, and graph neural networks help us learn from both the attributes of each entity and the structure of the network around it. So in this session, we'll show you how connected data can reveal suspicious communities, how GNNs can score account based on network behavior, and how this approach can help investigators focus on the highest risk mule account activity faster and with more confidence. My name is Sebastian Mansell, and I lead our AI product team here at Tiger Graph. And today I will start by setting the business context, why mule activity is such a difficult problem, why traditional fraud detection approaches often miss hidden rings, and how graph and AI can really change the way we detect and investigate this type of fraud. Joining me is Abraham Chandi, our AI solutions engineer. Abraham will take us deeper into the GNN approach. He will show how graph neural networks can learn from a relatively small set of labeled fraud cases and then use the broader graph structure to score accounts that have not yet been flagged. He will also show us how how much hidden fraud the GNN can uncover. And then he will walk us through the implementation details and do a live demo so we can see how all this works inside Tiger Graph. Our goal today is to keep this practical. We'll connect the fraud challenge to the technology. We'll show how the approach works and explain why GNNs are especially well suited for detecting mule networks hidden inside the connected data. So to understand why mule detection matters, it helps to start with the scale of the problem. Money laundering is not a small, isolated issue. It represents $5.5 trillion in illicit volume every year. Now, that's between 2 and 5% of global GDP. So that means a massive amount of criminal activity depends on the financial system to move, hide, and legitimize stolen funds. Now, a key part of that activity is the money mule. A mule account receives stolen funds and quickly passes them on, often through transfers, withdrawals, crypto exchanges, or additional accounts. Almost every scam needs this step because criminals need a way to move money out of the victim's account and into a network they control. Now, the challenge is that detection remains extremely difficult. Authorities intercept less than 1% of illicit flows, which means most suspicious activity is never successfully stopped or recovered. At the same time, the number of flagged mule accounts is already huge. More than 2 million mule accounts have been identified across 257 banks, and that is only a fraction of the global financial system. So the real number is much, much higher. Now, for financial institutions, this creates 5 major pressure points. 1, regulators expect more. 2, fraud tactics are evolving faster. 3, reputational risk is increasing. 4, compliance costs continue to rise. And finally, customers face more friction when investigations are delayed or when legitimate activity is flagged incorrectly. So the takeaway here is that mule activity is both a massive financial crime problem and it's an operational problem as well. Banks need better ways to detect hidden networks earlier, prioritize high-risk accounts, and reduce the manual burden on fraud and AML teams. So now that we've established the scale of the mule problem, the next question is, why do today's defenses still miss so much? Now, the main issue is that most detection systems look at one account at a time. They score each customer, account, or transaction based on its own behavior. Now, that can work for obvious fraud, but mule networks are designed to avoid looking suspicious individually. Each account may appear like an ordinary customer, even though the group behavior is highly coordinated. The second limitation is that many graph-based searches still require a starting point. They are good at expanding from an account that has already been flagged, but they may not discover a brand new mule ring if no account in that ring has been identified yet. So in other words, traditional graph search can help investigate known risks, but it may not always surface unknown networks. And then the third challenge is that data is trapped in silos. Mule activity often crosses accounts, institutions, devices, identities, merchants, payment channels, and that makes it harder to see the full pattern. And this is why mule detection is fundamentally a network problem. The suspicion signal is not always in one account. It is in the relationships between accounts, transaction devices, and behaviors. And that is where graph neural network comes in. A GNN does not just evaluate one account in isolation. It learns from the broad network structure. It can detect suspicious pattern even when individual accounts look normal. So traditional rule-based detection is useful, but it's incomplete. Rules work well when we already know where to look. So for example, once we have a confirmed mule account, rules and graph queries are effective at expanding the investigation. So we can trace direct connections, we can identify related accounts, follow the money flow, and build out a case around a known fraud. Now, this is valuable, especially for cases of expansion and for follow-up analysis, but the rules start to break down when fraud ring has not yet been exposed. And so in a dark ring, there may be no confirmed mule account to start from. And that means the ring can sit outside the search. So as a result, coordinated mule behavior can remain hidden until another signal finally reveals it. So the limitation is not that the rules are bad. The limitation is that rules need a known pattern, a known threshold, a known starting point. But mule rings are specifically designed to avoid those signals. They stay below the thresholds, they spread activity across multiple accounts, and they avoid obvious links to known fraud. So this is why pattern-based detection is needed, and this is where learning-based detection comes in. So rules are powerful, but they can only catch the fraud patterns we understand well enough to define. So they are fast, explainable, and precise. If we know the behavior we want to catch, for example, a large transfer out or a device shared by many accounts, we can write a rule to detect it. But fraudsters adapt. They change behavior, they spread activity across multiple accounts, they rotate devices, they just stay below the known threshold. So a new scheme can bypass rules simply because it doesn't match an existing pattern. And graph neural networks takes a different approach. It learns from examples of known fraud and legitimate accounts. It combines account behavior with graph signals such as money flow, shared identities, and just the network structure. So that allows the model to score accounts that no one has flagged yet. And so the point is not to replace rules. The point is that this is a complement that graph-based learning can detect suspicious mule patterns before the ring is already known. So with this context, I'm going to pass it on to Abraham to walk us through the training.
Thank you for that introduction. Let me just share my screen real quick. And okay, hopefully my screen's visible. Let's talk about the training real quick. The GNN wants to learn from fraud signals, so it can discern a fraudulent account from a regular account. So, what kind of signals do you want to do you want to share with the GNN? Logically speaking, you want to look for those patterns where a fraudulent account is vastly different from a clean account. Examples can be money flow. For example, if a fraudulent account could probably have cash in roughly equal to the cash out, and it leaves fast. Or the timing, a burst of activities for a few days, and then the account goes quiet. Or a structural, for example, the account sits in a type loop of accounts that pay each other. Or identity sharing, where one phone or device sits behind many different accounts. So let's talk a little bit about how it learns. So you want to train the data set on a few confirmed Mule accounts that are available to you and the broader pool of unlabeled accounts. So you want to learn which patterns look like the Mule behavior so that you can score on an unlabeled data set. And that brings me to my point where there should be no memorizing. The GNN shouldn't actually memorize the values that are given. In that case, it won't be able to generalize on new data. So we want to ensure that doesn't happen. And what we get in the end is we're able to score a new account or unreviewed account and return a fraud risk ranking. For example, account Z, if it was not in the training earlier, you can pass it into the trained model and get a risk score of 92%, which in this case, it indicates likelihood of being fraud. Let's talk about the training data set real quick. So the fraud patterns in the training data set, which is synthetic, it was divided across 5 different patterns under a single label of fraudulent. So in this, we had layering networks that included chains, cycles, funnels, and many-to-many webs that bury the money trail. We have money mules where you have pass-through accounts that receive illicit funds and move them on. You have structural and smurfing accounts where you have large sums of money split into smaller transfers to dodge reporting thresholds. Then you have other patterns which could include the one-off uh, fraudulent fraudulent person where people are scammed out of their money. And then you have trade-based fraud where transfers are disguised as ordinary business or invoice payments. So essentially you have one label but several patterns in that label that we labeled as fraud. Now the hard part is in real life, in a real bank situation, you are able to catch a few fraudulent accounts with your fraud rules, but like there are a lot more accounts in your data set that are unlabeled. So you have confirmed cases of fraud, and then you would assume that everyone else is unlabeled. And what we did in our synthetic data set was, since we knew all the fraudulent accounts that we were making, we had to run a masking algorithm to hide most of these accounts from the GNN model, and we would use them for evaluation at the end. So let's talk about the results. After we ran the model from end to end, we got some really good results, and you can see that from here. Normally, we don't show accuracy as a good or renewable metric that we want to see. So here we're looking at the recall, and we want to measure this against a random review. Since the total fraudulent accounts in this data set was around 0.02%, your random review was quite bad, and our model actually learned about 100 times better than the review, essentially. You can see that if you were to review 1% of the scored accounts, you would reach up to 74% of the entire fraudulent data set. So most of them would be caught by just this much. And another metric that you want to look at is the ROCAUC, which is 95%. And what this means is, given a random pool of one clean account and one fraudulent account, the model is able to distinguish between them 95% of the time. So that means there's very little overlap between the two kinds of accounts. let's finally, we can talk about the implementation so you can start to do it yourself. Um, so we have one graph in Tiger Graph that we were able to model this bank data for. If you look at the vertices and edges that we have your party vertex and we have your account vertex. Party can be a company or a person, and then you have PII vertices that are attached to the party vertices. PII stands for personally identifiable information, such as your address, your date of birth, your name, your email. And we have another one called the min hash, which actually uh, supports fuzzy matching. So John Smith with JON would also match with JOHN, John Smith. So that's the fuzzy searching. And essentially, one party that has enough PIIs in common with another party would be resolved into your entity resolution model. So we have that as well here. And then we have the identity sharing of vertices, like your phone, your IP, your device. And these are used as signals. So if multiple people share the same phone or IP while they're making transactions, you can pass that into the model directly, and that goes into a signal. Now, you want to look at the account vertex as well, and you have the has paid edge. So in theory, you can have account A pays account B, and you can have that information and that's very useful when you put that into a model. You also have your account. So it doesn't particularly model if account A pays account B, but account A and account B have a sort of relationship where they exchange money with each other. That's an aggregated feature. And you would also pass that into something called a weakly connected component, which is an algorithm that we use to find out if there are rings or if multiple people are used to work, sending transactions with each other. We'll also look into the kinds of signals that we mentioned before, and we can do that right now. So there are structural signals and they're all stored on the account vertex. So examples of this can be structure. And here you want to look at page rank, you want to look at community size, you want to look at degrees, triangle clustering. I'll get to all these in a second. Then you have your money flow, like you're going to look at how much money goes in, how much money comes out, all the ratios involved. Here, there are 8 such features that we have here. And then you want to look at temporal features, like you want to look at things like burst, span, how quickly they are. We actually have 11 different kinds of features. And then finally, we have identity. And you want to look at how many devices are in common with parties and so on. And all these are going to be passed into your into your GNN model. And the kind of GNN model that we use is a graph attention network. That's the GAT model that we have here. So let's actually talk a little bit more about the feature engineering queries. One good feature engineering query is money in versus money out. So each and every account will have sum of money in, you have sum of money out, and you can have the ratio of money in versus money out. And the reason why you want to do this is because, well, it's usually predictable for a normal account. But if you see really like a spike in that for a fraudulent account or mule accounts, these will be vastly different from a normal account, essentially. And another one is triangle counting. So what this says is if account A has relationship with account B, C, and D in terms of transactions, if you move forward into account C, does C also have a relationship with B or D? If so, then your triangle count increases. And this and real PEs like employers, shops, and landlords don't usually pay each other. So this can sort of have a signal. It might not necessarily, but it can. And another one would be shared identifiers. For example, if you have your party has a phone that they share with multiple parties sharing the same phone, and these parties have accounts as well. So in this case, you'll have device share account of 3, and that will be shared on your account as well. So mules usually have multiple phones associated with one IP. So this is just an example of your kind of feature engineering features that you can have. Another one is your timing. So timing for a legitimate account can be fairly regular and steady. You might have uh, you might spend money for going to a breakfast joint that you're comfortable with, or maybe a bodega. But mule accounts have burst ratios, so they have large periods of inactivity, and then you suddenly spend a lot of money, and you want your model to be aware of these situations as well. So you're passing them into your model. Another one is for structure and ring membership. Now, the page rank is one of those structure that shows the importance of an account in the entire neighborhood. So how many people are paying this account versus how many accounts this one is paying, right? And all and one that have higher page rank scores are considered more important accounts. And this doesn't mean necessarily that a higher page rank can imply a higher mule, because you can just have a merchant with a very high page rank, but this, in addition with all the other features, can possibly signal some sort of a fraud or a mule. And now we have the WCC, which I will actually get into later. But here you look at the ring size or the community size. If more people sort of are interacting with each other more regularly. So let's actually move on to the demo real quick. We have Tiger Graph here. We have Graph Studio, where I have to log in again. If you excuse me for a second, do that real quick. And so let me share my screen again. Okay, my screen is visible. You can see the schema here on Graph Studio again. As usual, we have our party vertex, and we have a same as edge here. So how this works is you first want to look at all the PIIs of them. As you can see, you have your birthday, you have your several min hashes, and name, email, phone number. If multiple parties have shared PIIs with over a certain threshold, they all get into the same as edge, and these are all resolved into the resolved entity vertex at the end of that algorithm. So that's your entity resolution site right here, and then we can actually look into the account vertex itself. Now, all the attributes of the feature engineering queries are actually stored on this attribute. TigerGraph has the ability of storing properties over here. So, for example, you can see things like page rank, community size, and so on. We have several of these over here just to give the account more context into how this particular vertex operates. And then you can look at the has paid edge. So this exists between two accounts. For example, you have account A has paid account B. The two main properties here that you see are total amount and the total number of transactions. Now that's fine. That's a very concise way of reporting that. But suppose you have about 6 months of activity of look back data in Tiger Graph. How do you show the burst ratio? How do you show all these temporal features that I talked about earlier? So we designed a solution particularly for this, and we decided to use a feature called bin days, and this actually sort of separates has 14 days equally spread out between that 6 months. So if it's 6 months, you would have 12 bins, assuming that this is half a month, right? So and for each of this, you have a list object, which is an ordered list of essentially numbers, right? So you have your total amount and your number of transactions, but you have them segregated into batched 14 days. And your GNN model would like this very much. You can get context, and you can derive features, and you can pass them in directly as well into your GNN from here. So similar to the same as edge, you have your account edge, which sort of scores all the accounts that have interacted with each other, and then you pass them into a ring, and then you pass them into the connected component, which is weakly connected components. Again, we can talk more about that soon. I just wanted to show you the explore graph features because we can probably look at an exploration. So this is an example of an exploration that would go directly into your model. So let's look at this real quick. So we are starting from this vertex. So starting with account ending with 813, and you look at all the neighbors of probably capped to 15 different accounts. So you look at all the neighbors of them, and then that's all this is one hop. And then you look at at one of those neighbors here, and then you look at all their neighbors, and you're passing all this contextual information right into your model, into your GNN, directly from Tiger Graph all the way to the GNN. And another example of this is we can show the device connections here. So here is the device connections. I can probably force it here. And for example, if you have this customer here and they have two accounts here, they have one device here, and oh, look, they have another device, and this device is connected to many other customers. Now, sure, they can probably be part of the same family or the same group, but they could also be a fraudulent case. But you're not actually doing an investigation on each and every one of these. Instead, you're batching it and you're sending all this data directly into your GNN model, where your GNN can train and learn on this, whether or not this was actually a fraudulent account. Now, let's look at a couple of queries. So, of course, so this whole project of running your GNN from end to end, Tiger Graph, requires a lot of queries. It requires a lot of information from the graph. And some of these queries were used to serve them directly from Tiger Graph to your GNN machine learning workbench. But we can actually talk about a couple of queries that we ran. So number one is for your entity resolution. The first step, if you recall, was passing it into the same as edge. So we can look at that. We have match parties query here. And so what this does is it looks at all the PIIs that we have here, like email, and sort of judges them based on the weight. So you can actually do this on your own too, but for my intents and purposes, I put the email weight of 1 and I put the threshold of 1. So that this tells you that if you have an email weight of 1, that's it. These two people are the same person. And your other weights are slightly less. For example, phone could and birthday, it's very less. But essentially, what this algorithm does is it walks through all the edges for PII, and then it sort of adds up these weights. It scores them and it adds them up depending on how many times it comes in, and then. If you cross the threshold, then it passes it into the same as edge. That's what the algorithm does. The second step of your entity resolution is to unify and to take everything from the same as edge and pass it into the entity resolution. So the entity resolution vertex will now be a proxy of the party vertex, but now it'll be deduplicated. So you'll have resolved them already. So that is the unify parties here, and that's exactly what it's doing here. It looks at all the people here in the same as edge, and it passes them on to your entity resolution. So the next one that we can look at is the weakly connected components. Over here, that's another important algorithm that we do. What a weakly connected component does is it looks at a larger graph and it sort of divides it into smaller subgraphs. So if you look at these relationships here, the account relationships, or the account has paid relationships, that is a graph in itself. And you want to divide that into smaller subgraphs based on who's interacted with whom. For example, if you have a smaller cluster of like 15 people and the money keeps flowing between them, then that sort of gets into your community, and then you have a community size. And how that happens is step one, you have your account with weights. You have a minimum edge weight. I actually set this for 1 for my intents and purposes, but sometimes you can have really, really big communities, so you can increase this for yourself. And basically, if you had one transaction with somebody else, then everything goes into your account weights here. That's step one, very similar to your NG resolution query. And the second step would be is our standardized WCC query that TigerGraph has in the data science library. And we basically take all the accounts that are in here in the account weights and pass it into the connected component vertex type. So essentially that does it, and you can actually identify rings from these queries alone, but you don't want to take that as a hard and fast rule. You want to give it to your GNN as additional context. So I think that's all the other queries are about sampling, about feature generation, as we've gone before. So I think for now, I think we're done with this side of the presentation. I will pass it on to Sebastian so that he can close.
Thank you, Abraham, for this very detailed details on the implementation. All right, so we'll switch it back to the presentation. You can all see my screen. So let's look at the end-to-end flow. All right. So the process starts inside TigerGraph, as Abraham has shown. This is where we store the connected data, accounts, payments, devices, identities, the relationships between them. And that matters because Mule detection is not just about individual attributes. The strongest signals come from how accounts are connected and how behavior spreads across the network. Now, once the data is in the graph, TigerGraph then computes the signals the model needs. So these are all the algorithms that Abraham walked us through. And then graph queries and algorithms, they turn raw relationships into features such as money flow behavior, shared devices or phone numbers, connected components, page rank, and other structural patterns. And those graph-derived features are then exported to the GNN. So what the GNN does is first, it trains based on the labeled graph features. So these include known fraud examples, known good account examples, and then those graph-derived signals. So the GNN then uses the data to learn what mule behavior looks like across the network. Second, TigerGraph sends the updated transaction and data for scoring and inference. So we actually export these fresh graph features for new and updated accounts. And then the GNN scores these accounts and produces a risk score. So these scores are then brought back into TigerGraph, and they're attached to the account, ranked by investigators and viewed in the full graph context. So the last part is important because the output is not just a score itself. Investigators can see the surrounding money flows, the shared identities, connected accounts, ring structure that explain why an account was prioritized. So TigerGraph here plays an important role. It stores the connected data, computes the graph signals, it feeds the GNN for both training and scoring, and then brings the results back into the graph for investigation. So with this synthetic test that we performed, we were able to show how graph signals and GNNs can really help identify Mule accounts that were already known, that were not already known during training. So in the test that we performed, we scored 91,018 accounts. Now, the goal was to see whether GNN could rank Mule risk accounts above clean accounts, even if when it only had a small number of labeled accounts, Mule accounts to learn from. And the result was a 95% AUC. So in practical terms, that means that the model did a really good job at separating Mule accounts from legitimate accounts in the ranking. So if we compare one Mule account with one clean account, the model ranked the Mule account higher 95% of the time. That's what this AUC figure means. Now, the most important point is that we only provided 88 Mule accounts for training. So we intentionally kept that number limited so that the model could not simply memorize known Mule accounts. It had to learn the underlying graph patterns associated with mule behavior. So the model did not, just rediscover accounts it had already been told about. It had to apply what it learned to accounts it had not previously seen as fraud. And this is where GNN and graph really matter, because the graph provides the network signals, and the GNN learns from those signals, combines them into Mule-like behavior, and then uses that learning to prioritize unknown accounts for investigation. So what we really want you to take away from this session is that Mule fraud rarely shows up in a single account. It lives in the pattern across many accounts. An individual account may look normal on its own, but when we look at the broader network, the money movement, the shared devices, shared identities, timing, and structure, the risks become much clearer. And this is where graph plus GNN really help. The graph captures the pattern. The GNN learns how these signals combine into Mule-like behavior. And TigerGraph supports this workflow end-to-end. It stores the connected data, computes the graph signals, sends the features to the external GNN, and brings the risk score back into the graph for investigation. So the message here is simple. Fraud lives in the pattern. The graph captures the pattern, and the GNN helps surface Mule account that rules or seed-based searches may miss. So this concludes our webinar today. Thank you again all for joining. We encourage you to try TigerGraph on your own by going to tgcloud.io and getting a free session, or by scanning the QR code. And you can also access the GitHub repo shown here to explore the Mule Pattern Learner and experiment the GNN training workflow that Abraham showed us on your own as well.